Um, well, thank you for joining today. Today I'm going to be talking about how do we automatically tighten semi-definite relaxations for problems that sort of show up naturally in robotics. So as mentioned in an earlier lightning talk, quadratically constrained quadratic programs show up a lot in robotics. So all a QCQP is I've got some quadratic objective and some quadratic equalities and inequalities, and I'm assuming that none of these are positive semi-definite. So none of these, so this problem is not a convex program. And these have been used in a variety of settings in robotics. We've used them in contact-rich planning. There's been prior work using these for robust estimation. And you can also use QCQPs to perform things like inverse kinematics. Part of the reason they've become increasingly popular in robotics is that even though QCQPs are non-convex and really hard, there's a very popular, simple semi-definite relaxation you can write, where this is a convex program that provides a lower bound on the original program. And in a lot of instances, this convex relaxation, which is very fast to solve, actually gives you the right answer. And so for those who are familiar with semi-definite relaxations, this is actually the first level of the sums of squares hierarchy. And so everything I'm going to talk about today applies more generally. On the other hand, this short semi-definite relaxation is actually sort of the only level of the sums of squares hierarchy that's proven to be fast enough for applications in robotics. And so that's why I'm going to focus on that one today. Unfortunately, sort of in its standard form, the short semi-definite relaxation is frequently too weak for the problems that we care about. So typically when you do sums of squares relaxations, if it's too weak, you increase the degree. But an observation that's been made over and over again in practical applications is that if you have a QCQP and you add a completely redundant equality constraint to it, that redundant equality constraint might actually show up in the actually ends up showing up in the semi-definite relaxation. And even if this constraint is redundant for the problem on the left, it's not necessarily redundant for the problem on the right. The sort of famous example of this in this literature is from Hank's teaser paper, where he gives a QCQP formulation of sort of robust rotation estimation. And it's very important that he adds this redundant equality constraint. And all you really need to take away from this is that these two programs have the same feasible set. When you take their convex relaxation, they give very different performance. A shift left is good because it means that I'm getting closer to the true optimal value and I'm recovering the optimal solution more often. And in blue, you're seeing that the strengthened formulation performs much, much better. Now, finding these redundant constraints has typically been done manually, and it constitutes a very important part of the contribution of many. On the other hand, in this work, what we show is that we're going to give a method for finding all of the possible redundant quadratic equalities you could possibly add to the semi-definite program. And we find only the ones we can find cheap. Perhaps more importantly, we're only going to end up adding those equalities that can provably tighten short semi-definite relaxation. There are a lot of things you could add to the program on the left that will not help, and there are a few that are going to be very, very powerful. Finally, the method that we're going to propose is very fast. It's fast enough to be used as a pre-processing step before solving any SDPs. And that's really important in comparison to things like computing Grosvenor bases ahead of time for those who know what those are. And finally, the method does generalize to arbitrary polynomial programs. And so if that's what you're interested in, then we can talk about that later. So the first thing I'm going to talk about is how do you actually generate the set of all possible implied equalities? There's a very standard theory known as sort of the ideal generated by these by the original constraints. And basically what you can do is if you give me a list of polynomials mu I and you ask, is some constraint redundant? I can convince you of that fact by taking these polynomials and writing my implied quadratic in terms of the original generators. This should convince you that this is redundant because this is zero on the set I care about and this is zero on the set I care about. I know I'm moving fast, but the key takeaway here is that you can actually search for all implied equalities that you could possibly add to a program by simply solving a linear system. There's a linear parameterization of all of the implied equalities. Now, perhaps more importantly than parameterizing all of the implied equalities is which ones can actually tighten the relaxation. And in the workshop paper, we give a very simple condition based off of sort of the degree of the polynomial that you want to add as an implied equality that shows whether it can or can't strengthen the relaxation. And again, the key takeaway here is that it's going to be a linear condition in the implied equalities. So specializing this again to QCQPs, you're going to see that a new implied equality can only strengthen short semi-definite relaxation if that implied equality is not in the span of the original matrices used to define my problem. And again, the key takeaway here is that both of these conditions are linear. The set of all possible implied equalities that you can add is linear in the set, you can parameterize them linearly. You can also parameterize the useless ones linearly. And that means that after fixing a certain degree, and this is what I meant by found cheaply, you can compute all of the useful implied equalities that you can possibly add to a QCQP by solving just one big linear system. So the first thing you might ask is, does this procedure even sort of recover the useful implied equalities that are found in the robotics literature? And the sort of key thing that we show is that even at very low degrees, we're able to recover sort of all of the known instances of tightening equalities that have proven practical in robotic settings. Perhaps more importantly is, why is it important to only keep the useful implied equalities? If you added everything you could possibly add, you'd be adding over 22,000 constraints when only 24 of those are actually useful. So if you add everything, your SDP solver is going to slow to a crawl. But if you add only the useful ones, you increase the solve time by almost nothing. Finally, because every step of this is based off of simple linear algebra, it takes a fraction of the time to actually generate all of these useful implied equalities compared to actually solving the SDP. So it's worthwhile to do this before you ever solve an SDP in the first place. So the main takeaway is that QCQP relaxations can be strengthened automatically by finding implied equalities that actually change the SDP. And it's a very simple three-step procedure. The whole procedure relies only on simple linear algebra, and so it's fast enough to actually be used as a pre-processing step. And finally, the method actually generalizes any polynomial program you could possibly want. The construction just becomes a little bit more delicate and involved.